By the way, this chapter 9 will be considerably shorter than chapter 5. So there's much fewer topics to deal with. There are still some difficult topics we have to deal with, but I think when I was looking things out, it looked like about 6 lectures maybe that I'll need to do chapter 9. I think that'll be considerably, 2-3 less than we had for chapter 5. So our topic for chapter 9 is going to be on rational functions. So let's kind of define what we mean by a rational function. So we have this technical definition for a rational function, but basically what it boils down to is a rational function is just like a polynomial divided by another polynomial. Now, we're a little bit careful with that because we remember that polynomials include things just as well as numbers, right? 7 is technically a polynomial. So we have these extra couple of restrictions on what these polynomials look like in our rational function to make sure that we don't include things like constant functions and linear functions that we've already kind of talked about. So the numerator of our rational function require it can't be 0 because 0 divided by anything is 0, which is a constant function. That's not what we want. So the numerator can't be the 0 polynomial, which is a pretty silly thing to be in your function anyways. And the denominator has to at least have an x in it, right? Its degree has to be greater than or equal to 1. If we allowed the denominator to be constants, you could have something like x over 2, which is just a linear function, right? That's 1/2 x. We don't want to include that. So we require the denominator has to have degree at least 1. So you have x's in the denominator always for rational functions. Is everybody okay with that idea? Okay. So it's basically just saying polynomial over polynomial, right? And we just discard these trivial situations that that would just be something we've already talked about, is all the requirements that are going on there. To just give us a little bit of an overview, we're going to talk about 4 major topics. I meant 3 major topics. So we're going to talk about simplifying. So today, we're going to do reducing, multiplication, and division. Friday, we're going to do addition and subtraction. When we come back, we need to do solving. That's like 1 day. And then graphing. This will probably be 2 days. We're going to look at 2 situations. One of them is the simple rational function, and the second one is the general rational function. That tends to be the trickiest topic, and is kind of going through the details and getting a good graph for a general rational function. This is just like a little bit of an overview, though. So it looks like, when I was counting things out, it looks like, 5 or 6 lectures, depending on kind of how things fall. Now, we'll take more than 5 or 6 days to do this, because we'll have some days to work and review and all that kind of jazz. But that should be considerably less than what we spent in Chapter 5, which was, 6 weeks or something, right? Basically all of January and half of February we spent kind of walking through that. And I think we even started a bunch of that even before break, right? So that was a big chunk of time. Basically, I just want to give you a little bit of a picture of kind of what we're going to do and what to expect, and things going on there. Okay? Okay, so we have 3 topics to talk about today: reducing, multiplication, division. So we'll start talking about reducing here. So reducing a rational function is basically the same idea as reducing a fraction. So let's go back into our time machine and go back to, late elementary, early middle school, when we would have talked about reducing fractions. Let's say we have the fraction 2. It's pretty something very easy. What does this reduce to? 1/2, right? What did you do kind of internally to do that reducing? What was the steps that you did in your head there to do that? Anybody? Okay, what did you say? I'm sorry, I couldn't tell. With the masks, it's impossible for me to hear, to see who's talking. And then I'm so deaf, I have a hard time. Okay. Yes. So one way of thinking about that is that we can do like a prime factorization. So 2 is prime already. 4 is 2 times 2. And then we can reduce kind of that way, right? Everybody agree with that? That is the method that we want to kind of employ here when dealing with rational functions. Okay? The reason we want to do that, as opposed to I'll just divide the top and bottom by 2, right? Like some of us probably learned how to reduce fractions that way in your elementary or middle school, right? The reason that method is going to be bad for us is if we start having polynomials. Is it easy to see what the divisors for a polynomial are going to be on sight? Definitely not, right? If it was easy to do that, Chapter 5 would have been a breeze, because we spent most of Chapter 5 trying to figure out divisors or factors for a polynomial, right? So the second, or this method, who was talking to me? I still couldn't really even tell which girl was talking. It was, I'm so sorry, but there's no mask and you weren't moving. You're just moving your lips or whatever, but I covered and I couldn't see them at all. So the method that Emily described is good for us because to factor a polynomial under certain conditions is very easy, right? We have a lot of factoring shortcuts that are available to us that allow us to factor some polynomials on site, right? Basically things that fell into that factoring tree were things that we could easily do on site, which is what primarily we'll be running into in this chapter, polynomials that we can factor on site. So let's look at a couple of examples here. So let's say that we have times. Actually, you know what? I'm going to make this much easier for the first time. I don't want to do that. There's some other points I want to make that are easier to make with a simpler thing. I'm sorry, guys. You forgive me? Don't lie if it's not true. Forgive me. Let me know. Let's do that. That's a better first example. Okay. So, well, can I just do this? Never. What's wrong with what I've done here? How is this different than what I did before? I just crossed off the 2's before. Why can't I just cross off these x squareds? What's different? Or what's the important piece that's different? Yes, Amanda. Excellent, yes. So here, each of these 3 terms are being added. In this problem, they are being multiplied. So it'll cancel things off when the only operation going on is multiplication. Addition, not so much. So that is a temptation you must unlearn immediately. It is a major problem. There's no recovery from doing that if you do that in a problem. You must not do that. It's never, ever okay to do. And if you think about it, if we go back to like fractions, if I have like 3 plus 7 over 3, we know that's 10 over 3, right? If we were allowed to do what we did, it'd be equal to 7, right? Which is clearly nonsense. So if you start crossing things out and when there's addition between them, we need to meet after school and do some currency exchange. I will give you 10/3 of $1 and you'll give me $7. And we'll just do this over and over until I have all your money. Sound fair? Don't shake your head like, yes, that's fair. That's not fair at all. Just don't do it. Okay. So what we do need to do is somehow turn this addition problem into a multiplication problem. How do we do that? By factoring. So x squared plus 7x plus 12 looks like a chapter 4 factoring problem, right? Its leading coefficient is 1. It should be something we can factor on site. What are the 2 numbers that multiply to give us 12 and add to give us 7? 4 and 3. So this becomes x plus 4 times x plus 3. Remember, the order doesn't matter that you write the things in the parentheses. And how does the denominator factor? Good. X plus 5 times x plus 4. And then what can we reduce? The x plus 4s. Notice what we really have here now that we factored is we have 2 things that are being multiplied in the numerator and 2 things that are being multiplied in the denominator. The only operations going on outside of those sets of parentheses is multiplication. So we can cancel a full set of parentheses, right? Can we cancel things inside the sets of parentheses? No, because there's operations other than multiplication going on inside the sets of parentheses. It's either all or nothing. Does that feel okay? So when we cross these out, really they're becoming 1, right? Because they're dividing away. And what we're left with is x plus 3 over x plus 5. Can I cancel the x's? No, why not? Because it's addition. This is just where we end. Everybody's okay here? You shouldn't be, because this is what I've written is technically not true. There is a small problem going on. And it's very subtle what the problem is. So let's think back here. When I write a fraction, can I put any number over any number and have it be okay? Think hard. Any number over any other number, is that okay? No. What's the problem? Okay, 0 is a problem. Where is 0 a problem? In the denominator. Very good. Everybody's okay with that? Remember, anything over 0 is undefined. So if these two fractions are equal, like we've written then, any value I plug in for x on the left-hand side should give me the same value on the right-hand side. You guys agree with that? That's what equal means. Okay? So let's try doing that. I'm going to plug 4 into each side and see what I get. Well, on that side, I get 7 over 9. So 16 plus 28 plus 12 is 30, 40, 56 over 16. Well, I meant to do -4. Eep. So that gives me -1. -4 gives me 16 minus 28 plus 12. So that's going to give me 0. And then 16 minus 36 plus 20. Are those two things equal? Is undefined equal to -1? No, right? Now, every other value of x that I could have picked, they'd still be equal. But this one value of x, they disagree at. So, to really have a complete answer, oh, come on now, computer. We'd have to say that it's when x is -4. Now the question that you should be asking yourselves, okay, Mr. Kulik, I see that -4, they're not equal. How did you find that? Right? That's the question. Okay? So you've demonstrated that this can happen. I can reduce something and they not are equal for any value of x. There might be some values of x where the two things that the beginning and the end are not equal anymore. How do I find those things? Well, look at the middle. The middle is where we've transitioned from the beginning to the end, right? What did we cross off in the middle? X plus 4. What do I get if I set that equal to 0 and solve? I get the -4. So those values at the end, these restrictions, which is what we'll call them, we can find by taking the pieces that we've reduced completely from the denominator and set equal to 0. Notice that I'm saying reduced completely from the denominator. Let's look at another example where we can really illustrate that. Okay? All right, let's say we have x squared minus 9 over x squared plus 6x plus 9. What do I do first? I cross the 9s out? No. What should I do first? Factor. Good. What does and the denominator factors too? Okay. What can we reduce? X plus. When we reduce those, they become 1. So we're left then with x minus 3 over x plus 3. Are there ways? No. What's different about this one than the previous one? There's still an x plus 3 in the denominator, right? So if I plug negative 3 in, I'm going to get undefined on the left and the right, and everything is fine. So this one, there's no restriction. Now that's a little bit tricky and a little bit subtle. Did everybody kind of catch what happened here on this one? Edmund?
So they are equal.
Correct, yeah. Undefined equal to undefined, we're going to say is fine. Those are agreeing. Does everybody feel okay here? Okay. Let's do one more example, and then we'll move on to multiplication. Sound good? Actually, let's not make those 3s. 6s. Okay. What do we want to do first here? Factor. Very good. The numerator. To factor the numerator, what should we do? Okay, so that's the denominator. We can take the 6 out of the denominator. Sure. Oops.
2x the numerator.
Good, and then a 2x from the numerator. Okay. So then let's look at the stuff that we have left. X squared minus 2x plus 1. Can we factor that anymore? Yes, right? What does that factor to? Multiplies to give us 1 and adds to give us negative 2. Minus 1 and minus 1. Good. How about x cubed plus x squared minus x minus 1? Think back to your factoring tree. How many terms do we have here? 4. How do we factor something with 4 terms? We use, from the first group we can take out an x squared. From the second group we can take out a negative 1. So we have x plus 1 times x squared minus 1. Everybody's okay there? And the x squared minus 1 factors a little more also, right? What does that factor to? X plus 1x. Oops. I forgot the 6 here. Let's get that in there. There we go. Forgot about him. Okay. So let's reduce. What can we reduce? Okay. Anything else? Yes. Why could I reduce the 2 and the 6 there? Everything was being multiplied, right? So it's okay to reduce that like a fraction because it was all multiplication. See, we have to be a little bit careful here when we're doing the reducing, but it's still the same idea that we had with regular old fractions. Okay? Did a restriction occur here? Yes. Because you notice that all the x minus 1s are gone from the denominator. Did it matter that there's still an x minus 1 in the numerator? It does not. We don't care about the numerator at all when it comes to restrictions. We only care about what happened in the denominator. Did it matter that we crossed the 2 out? We reduced the 2. No, because it had no x in it, right? If it doesn't have an x in it, it can't cause a restriction. What do you guys think? Is this going okay? Again, if I'm going too fast or it's not clear, please let me know. I can slow down. I can talk about something some more. We can do another example. We can try to clarify. Alyssa.
Can you just explain again how you got the x equal 1?
Yeah. So if I look at the denominator at my reducing step, what I'm interested in are the pieces that I reduced. So I reduced on the 6, and I reduced the x minus 1, right? Now the 6 has no x in it, so that part doesn't matter. I reduced the x minus 1. There's no more x minus 1s left in my denominator, so that piece is going to cause a restriction. And to find that restricted value, I take whatever that piece is that I crossed out, set it equal to 0, and solve. And that's where I'm getting the 1 from. You're welcome. So again, when the restrictions come in, I'm only caring about the things that are reduced from the denominator, and I only care if it's been completely eliminated from the denominator. If there's another one of those factors still rolling around somewhere, I don't care about it. Sound good? Excellent. Let's talk about multiplication then. Yes? That jumped on me. So again, multiplying two rational expressions is just like multiplying fractions. So let's say we have 15 over 14 times 25, or 35 over 25. Do you guys remember how, go back in our time machine, go back to late elementary, early middle school. How do we multiply two fractions together? Cross multiplication is not the answer. That's a solving technique used to solve a proportion when you have one fraction equal to another fraction. So that's a solving tool, not a simplifying tool. Don't feel bad about answering that. Every single person, every single year, when I ask someone how they multiply fractions, that's the first thing anybody answers because it has the word multiplication in it, and it has to do with fractions, but it's not a simplifying technique. It's a solving technique. It just goes straight across, right? Numerator multiplies the numerator, denominator multiplies the denominator. You guys agree? If we do that, what's going to be the problem when we extend this to working with polynomials? Do you guys enjoy multiplying two polynomials together? No, right? That's kind of a pain in the butt, right? You have to build that grid or do the big FOIL. after you multiply two polynomials together, do they get more complicated or less complicated? More complicated, right? The degree gets bigger, the polynomial usually gets longer. Now you'd have to factor that to try to reduce it afterwards. Would you rather factor something that's more complicated or less complicated? Less complicated, right? So while this works, and reduces down nicely, there's a better way to do this when it comes to approaching things as rational functions. What's the other way I could do this problem? I could reduce before I multiplied, right? So 15 is 3 times 5. 14 is 2 times 7. 35 is 5 times 7. 25 is 5 times 5. And now we'll reduce before we multiply. And we get the same result. And that's going to be considerably easier for us to deal with when it comes to having polynomials instead of numbers, right? Even in this case, I had to get the calculator out to do 5 times or 15 times 35 because I just didn't want to do it in my head. I didn't need the calculator to do the second way, which is nice, right? Okay, so let's look at an example then. So let's say we have x squared minus 9 over x squared plus 5x plus 6 times x squared minus 4 over x squared minus 5x plus 6. First thing I should do is factor. Great. Tell me how they factor.
Both denominators, so they factor with the shortcut that we learned at the beginning.
Mm-hmm.
And the first one, we do x plus 4x.
Those don't multiply to give you positive 6.
Oh, okay.
Or add to give us positive 5.
Would it be, with the person, would it be no? The second one is 6 and negative 6 and 1.
Those multiply to give you negative 6, not positive 6.
Oh, 2 and 3.
There you go.
And then negative 2 and negative 3.
There you go. How about the numerators?
I don't know.
Okay. Someone else want to help us out? How to do the numerator? Mackenzie? Good. They're both differences of 2 squares, so they're easy to factor with that shortcut. Okay. Now it's time to reduce. What can we reduce? I'll start. I can do these x plus 3s, right? What else? The x minus 2s. What else? All of them, right? Everybody agree? So what does this equal then? 1, right? I have 1 times 1 times 1 on top and 1 times 1 times 1 times 1 on bottom. 1 over 1 is just 1. So I just box up 1 and say I'm done, right? Nope. Did I cross things out of the denominator? Were there restrictions that were caused? What are the restricted values that I generated there? -2, -3, +2, +3. I'm just going to write it as plus and minuses, though. We okay with that? Let's pause here for a moment. Was this multiplication problem appreciably more difficult than reducing? No. It just included a little bit more factoring in the beginning. But you'll see even when I wrote the factored form there, I wrote just one fraction, right? Did it matter where I reduced from which fraction to which fraction? No. Anything in the top reduced with anything in the bottom. I just wrote it all as one big fraction and went cross out crazy. Everybody feel okay on multiplication? Do we need to do another? Still kind of basically the same thing, right? Okay. How's this going so far? Do we feel okay? Not too big of a deal? I find these problems very satisfying where you start with something really complicated and you end up with something so much simpler. But that's just the nerd in me. All right. Well, let's go to division then, if we feel okay about multiplication. Guess what? It's going to be just like dividing fractions. Shocking! Does anybody remember how we divide fractions? Well, I remember from elementary school, my teacher taught us a rhyme so we could remember how to do this. She told us dividing fractions is easy as pie, flip the right and multiply. So based on that, we can just turn this into the multiplication problem. 14 over 35 times 25 over 6. And then we can just treat it like a multiplication problem like we did before. So 14 is 2 times 7, 25 is 5 times 5, 35 is 5 times 7, 6 is 2 times 3, and then we go cross out crazy. And we're left with 5/3. What do you guys think? Not too bad, right? Let's do this with a rational function, or expression, excuse me. Let's see, I want to be careful here. Then I want Okay. Now, doing a division problem. To do the simplification, not appreciably more difficult than a multiplication problem. Finding the restrictions in a division problem is a little bit tricky. So what we're going to want to do to make sure we get these restrictions correct is to do the factoring before we flip. So I'm going to rewrite this in a factored form, then we'll flip and reduce, and then compare before and after. Okay? So the numerator, we can take out an x cubed. The denominator, I can take out a 2. The next piece, I can take out a 7x to the 4th. And then I can take out a 6. I notice that x squared minus 4 is a difference of 2 squares. Oops. Bless you. You're welcome. And x cubed minus 8 is a... x minus 1 is linear, so that doesn't factor anymore. And x squared plus 2x plus 6, there's not two integers that multiply to give me 4 and add to give me 2, so there's no more factoring that I can do on that piece. So here it's fully factored. Now I'm going to do the flip. When we get to the end here, I'll go back and show you what previous step written down is going to be helpful. All right, what do we see that can reduce? Anybody see anything? Okay, the x squared plus 2x plus 4. Anything else? The x minus 2's. Good. Anything else? Okay. Anything else? The x's, right? Everybody okay there? All right. So my reduced answer is just going to be 3x plus over 7x x minus 1. Now to figure out my restrictions, I'm going to do something a little bit different because the division problem is a little bit confusing in that regard. So I want to be a little bit careful. So my fully simplified version is undefined when x equals 0 and x equals 1. Everybody agree with that? I'm going to go back now to this step and write down the values of x that make this fraction undefined. What are some values of x that make this undefined? 2, right? So things that would make the denominator 0 in the first fraction will make that problem undefined. Everybody agree? Okay, so I set that. If I set that piece equal to 0, what do I get? How would I find that? Yeah, Edmund? It's not positive 2 and negative 2, because that thing's not factorable, right? What would you have to use on it? Quadratic formula. But we don't really need to. Because in this case, where does that x squared plus 2x plus 4 come from? We got it when we factored a difference of 2 cubes, right? Does anybody remember what I told you guys about the solution to that quadratic trinomial that comes from the sum or difference of 2 cubes? Its solution is always imaginary. So does it contribute to a exclusion? No. Our exclusions are only real number values for x. So these guys give us imaginary pieces so that we don't care about them. Everybody's okay there? Now there's some other places that also create something that's undefined. Because remember, I cannot divide by 0, right? So if that second fraction is equal to 0, that's also going to make this problem undefined. Everybody agree with that? Because if I have 0 in the numerator of a fraction, that fraction is 0. So if I divide by that fraction, it's dividing by 0. So I get an x to the 4th. If that is 0, that's a problem. And also 1. Everybody's okay there? So if I compare these two, what is the thing that's different in this list than this list? Whatever's different is going to be our actual exclusion. In this case, it's just 2. So you guys feel okay? So again, doing the simplifying, not really any appreciably more difficult, right? Doing the exclusion, still kind of the same thing, but we have to be a little bit careful. And the piece that we have to be careful about is when we flip that fraction, there was stuff that, that's now in the numerator that if we crossed out, could be a problem later on. Is that okay? What do you guys think? You ready to try some of these on your own? I think this is a good place to stop for today. If you guys look in the... Oh, it's not in there yet. Let's put it in then. Get us an assignment in here. I think it's ready. I distinctly remember working on it anyways. Yup, there it is. We dump that into OneNote here and sync things up. You guys can spend the remainder of our time here together working on this assignment.